So the next topic we're going to cover is how threads run. And this will kind of explore a little bit about what's going on under the hood, although you don't have to be an expert in all this stuff, but it's good to know what's happening, and I'll explain why it's good to know in a second. When you start a thread, there's several layers involved, and actually probably dozens of function calls that are involved in starting a thread. And the different layers are the operating system kernel, the system libraries like libc, for example, the Java execution environment like the Java virtual machine or the Android runtime, as well as the class libraries that are defined as part of Java. So there's at least 4 layers, if not more. And of course, there's some hardware down at the bowels of all this stuff to do the actual computation. When you create a new thread object, when you say, new my thread, that actually doesn't allocate a lot of resources. It just allocates an instance that's capable of being used to allocate the more detailed and more expensive resources. In particular, what happens is a call stack will be allocated when start is called, but it doesn't get called at the beginning. The runtime stack and other resources for the threads are only allocated after the start method is called. So when you call start, then things start to run. And that's, again, I'm showing the machinery here down below. It's supposed to be gears and stuff that runs and does things. The start method can only be called once per thread object. So you can call it once. You've got to call it if you want the thread to run at all. But once you call it, you can't call it again without getting some kind of illegal state exception. Once start is called, the underlying Java execution environment, which includes, of course, the operating system and kernel and system libraries and so on, they all collaborate together in order to set up the runtime stack and then call the run hook method on the Java object that was just started. So that's where things start to get interesting. Once start is called and once run is running, then the newly created Java thread can run concurrently from the thread that created it. So there's always sort of a parent thread that creates another thread. And once the other thread's up and running and executing, they can both run concurrently. Now, sometimes the creating thread will wait and join with the other thread. Sometimes it won't. It all depends on what you're trying to do in your application. Within the run method of a Java thread, you can basically put any code there. So that's where you do your business logic or your application logic inside of run. Many windowing toolkits, in fact, pretty much all windowing toolkits, will restrict which thread can access the GUI components. And usually it's limited to the so-called user interface thread. So if you make a background thread, you can do an awful lot of stuff in there, but you typically can't call GUI operations in the background thread. And we'll talk later about how you communicate from background threads to the UI thread if you want to have something displayed to the user. In fact, the GCD examples we looked at do that quite nicely. In particular, in Android, the user interface thread and only the user interface thread can access the GUI components. And if you try to call GUI method calls from the non-user interface thread, then you'll get exceptions and chaos and insanity ensue and so on. And you can take a look at this link if you want to learn more about how threads are structured in Android. A thread only lives as long as its run hook method hasn't returned. So as long as run is still running, then the thread will be running. However, the underlying thread scheduler can suspend and resume the thread many times during its life cycle. And if you have a thread that runs for days or weeks or whatever, it'll undoubtedly be suspended and resumed many times by the scheduler to give other threads a chance to run. These scheduling operations are largely invisible to you as long as you follow proper synchronization protocols, which we'll talk about later. So you have to be aware of this only to the extent that when a thread is resumed and suspended, you need to make sure that any resources it's managing are properly synchronized to avoid surprise. If you want a thread to run forever, then you simply have it run a loop, like a while true loop or a for loop that just says for open paren, semicolon, semicolon, close paren. That will cause the thread to run forever. Of course, in reality, it won't run forever. It'll run until the program shuts down, but logically, it could run forever. Once run returns, the thread is considered dead. And there's several ways a thread can die. One is for it just to fall off main. So when it's all done, it fall off run. So it can fall off run, which will cause the thread to shut down normally. That's the typical way of doing things. Or if an exception is thrown but not caught anywhere within the call chain and it ends up percolating outside of run, then that will also cause the thread to shut down. And that's why you really want to install an uncaught exception handler to avoid surprises when the run method returns abnormally because an exception was thrown and not caught anywhere. Now, so that's basically how we start threads. That's how the threads run. That's how the threads go away. There's another very simple method that you'll need to learn for assignment 1A, if nothing else, called the join method. And that's used to allow one thread to wait for another thread to complete, for it to fall off main one way or another, either normally or abnormally. This provides what's called a simple form of barrier synchronization. We will talk a lot more later about barrier synchronization. You'll get a lot of chance to play around with barrier synchronizers in some other examples. But basically, barrier synchronizers are used to let one thread wait for other threads to finish, or to start for that matter. So think about something like, a starting gate for horses or runners on in a 100-meter dash or something like that. Threads can also simply evaporate. If nobody wants to join with them, when they're done, they will just disappear. And in either case, the Java execution environment will recycle thread resources. So after a thread is finished, after it returns, after, for example, it's been joined with, then the Java virtual machine will take all the resources that were allocated, like the runtime stack and any other thread-specific storage or whatnot, and give them back to the garbage collector so they're capable of being used for other computations and other data needs in the program. So examples of things that get cleaned up would be the runtime stack, thread-specific storage, and so on and so forth. So that's the end of the overview of how threads run. Again, you don't really have to be completely aware of all those details because there's some low-level stuff that we'll talk about later in the course. But be aware that starting a thread is a bit of an expensive operation. So you shouldn't start threads to run computations that themselves are very fast. Don't start don't start a thread to add 1 plus 2. That's overkill. Just add 1 plus 2. Now, if you're going to do some operations on big integers, which are arbitrary precision numbers, you might want a thread for that, depending on what you're trying to do. But make sure that the time needed to create the thread is smaller than the time for the thread's execution. And if that's not the case, then you need to reconsider whether a thread is what you actually want to do.